So, in the last lecture we discussed about estimation of damping for offshore structures. We said that the damping matrix can be either proportional to mass, where we said this can be A0m, or alternatively the damping matrix can be proportional to the restoring component force K, or it can be, let us say, A1K. In both cases we had problems, because if you look at the variation of zeta with respect to omega n, you will find that this is inversely proportional, whereas this is related to the mass, whereas when you talk about related to stiffness, it was varying increasingly. So, for any higher values of omega or any lower values of omega, either you consider this or this, you have got a drastic variation, and this did not match with the experimental studies conducted by people. Therefore, we said that let us result in a new model which is suggested by Rayleigh, and then Rayleigh damping says that the damping matrix can be the proportional of both stiffness and mass. Now, here the difficulty was with Rayleigh is you must select two frequencies such that these frequencies should agree on the same damping ratio. So, the plot was varied with a correction like this. So, two frequencies can be picked up which will have the same zeta value. So, if you are able to pick up those two frequencies from your given set of frequencies which will agree on the same damping ratio, then you can easily find out the damping ratio as well as Cn for a given problem. But again here, if you got multi degrees of freedom which has omegas much more than 2, then you want to have the damping ratio participation from all the modes. Then obviously you will see that in Rayleigh damping you can pick up only 2 at a time and keep on checking whether it is solving or whether it is validating for the remaining frequencies. If it does not validate, then you will change the zeta number and pick up couple of more frequencies and keep on iterating. You may arrive at a solution there that zeta may not agree for all modal participation factors happening in the analysis. So, if you want to include more than the two frequencies or more damping ratio, in fact for higher modes, then you should look for more classical damping which is given by Caughey. Caughey proposed a method by which can include higher frequencies also or higher damping ratios in modes. So, let us see how this can be handled. We will solve a problem and see how this can be applied to find out zeta and C for a given problem. Is there any doubt in the previous class for estimating C using classical damping proposed by Rayleigh? So, this is what we will discuss today in the lecture, that how we can use Caughey series for estimating damping. So, let us say omega and modes let us say satisfy a simple relationship which is K phi r, K again is omega square m. So, omega square r m phi r. Let us say we have a relationship which is satisfied. Now, I pre-multiply equation 1 with phi n transpose m k inverse. Sorry, k m inverse, phi n transpose k m inverse on both sides. So, let us do that. Let us say phi n transpose k m inverse k of phi r omega square r phi n transpose k phi r. Is that okay? Because m inverse m will become identity. Now, I can say coolly this as 0 for n not equal to r by orthogonality. So, equation 2. Let us say again pre-multiply equation 1 with square of this, that is phi n transpose k m inverse square on both sides. Okay. Let us do it here. So, phi n transpose k m inverse square of phi r, which can be omega r square, yeah, there is a square here, omega r square phi n transpose k m inverse k of phi r, is not it, of phi r. There is a m here, is it, or k? This omega square r m phi r, there is a m here. Equation number 1 has m here. Yeah, which will simplify to omega square r phi n transpose k m inverse k of phi r. So, phi n transpose k m inverse k of phi r is already 0 from equation 2. So, this is already 0 from equation 2. So, therefore, phi n transpose k m inverse square of phi r is 0. So, we are repeating this procedure by n number of powers of phi n k m inverse to the power L by repeating this procedure, we shall get the following equation, where I can say phi n transpose C L of phi r. So, I am replacing this with C L is 0 for n not equal to r, where I call this as equation number 3. Where C L is given by C L, which we use here, is given by K m inverse of K to the power of L of K. I will put it like this, where C L, this is what I am actually multiplying, 1, 2, 3, this is what I am actually multiplying in my whole process, for L equals 0, 1 till infinity. Now, I pre-multiply this equation the above equation with an identity matrix which is m inverse. So, C L now becomes m inverse K m inverse power L of K. I keep on expanding this for different values of L. I can expand it like this, m inverse K, m inverse K, m inverse K, and so on, is it not? So, I get a group now which will be m inverse K, m inverse K, m inverse K, like this. I can now write this as m inverse K of L for L varying from 0, 1, 2 to infinity. Let me call this equation number 4. This is nothing but C L. Okay? Any confusion here? Having said this, now instead of m inverse K, I will process the same equation back again from the first step with K inverse m, see what happens. Okay? We have reached equation 4, where I have processed the original equation of my orthogonality with m inverse K to the power L, that is what I did, is it not? I will do the same process again, but the multiplier is now going to be a different multiplier. Okay? I will remove this. Okay? So, the original equation what I had is similarly K phi r, which is omega square m phi r, I use r here, I pre-multiply this with phi n transpose m K inverse on both sides. I am just reversing it and follow the same procedure as above. There is nothing above here, but you have something in your paper, right. So, can you kindly do it and see what happens to me here? So, do it for once, do it for twice, and then you will know what is happening to my CL, summarize CL in terms of L. You will see that I get the same equation back. I get the same equation back. Now, the values of L will be -3 like this, will go to minus infinity. I call this equation number 5. I mean, this is a very simple mathematical process, you can do that, you will get this equation. Now, you combine 4 and 5. Let us see what we get. If you combine 4 and 5, I can write equation for CL as m of summation of L equals minus infinity to plus infinity AL of m inverse of k to the power L. I call this equation number 6. If you look at equation 6, basically the CL value is varying for a range of minus infinity plus infinity of L value, where L is nothing but omegas or omega squares, is it not? It is powers of omegas actually, because k by m is nothing but omega square. So, this hypothetically includes all omegas in a given model, is it not? But in reality, people have seen in the literature, I will give you the references back later, that after n number of terms, the independency of this term will not be existing, it keeps on repeating. Okay? So, the above equation is constrained to only n terms, because there will be only n independent terms. I will give you the reference, you can please see the reference later. So, I rewrite this equation again, instead of minus infinity to plus infinity, I will rewrite it now. Have you understood? Caughey model is including all the frequency ranges in my whole system, where Rayleigh was not doing it. Okay? That is the difference now, that is the deviation of this model from the Rayleigh damping. So, I rewrite this equation 6 with finite terms like this. Hence, CL now can become, I am using this left hand side board, it is easy for me to refer the literature. Is there any difficulty for anybody from the other side to see? You are able to see here now? So, let us say m L equals 0 to n minus 1. If there are n terms, there will be n minus 1 summation. Okay? AL of m inverse k of L, call this as equation number 7. Then, where n is the number of degrees of freedom. Okay. It is because of this problem, when you try to model numerically any structural system and find out the eigenvalues, instead of 6 degrees of freedom, you will get n number of eigenvalues. Okay. You have to see that how many of them are independent. So, I say that word independency related to my degrees of freedom actually. Okay. So, n is the degree of freedom here, and of course, ALs are constants. Now let us quickly see what happens to my AL value for different values of L. Let us say for L equals 0, C naught will be equal to which will be A0M. Can I write it like this? And for L equals to 1, C1 will be equal to A1, M inverse goes away, K. So, I am getting back the Rayleigh damping again here. Okay. For L equals to C2 becomes A2 K M inverse K. So, let us stop at 3 degrees of freedom and let us try to apply Caughey damping and see what happens, because we have an example where when degrees of freedom are 3. So, I will use it. I can continue for n number of degrees. So, we can very well see here in this equation or set of equations that the first two terms represent actually the Rayleigh damping.
K to the power L, then C1 should be A naught M plus A1 K.
No, I am looking how we can do that. So, CL I am trying to find out separately. When I will give a complete stiffness matrix, I will add all of them. So, I should say okay, I will come to this argument, let C will be A0M plus A1 K plus A2 of K M inverse of K. Is that okay? Right. So, I wanted these coefficients separately, I am going to use them in the next derivation. So, I am having this values. Ultimately, this is my damping matrix. Yeah, this will be 2. So, this is going to be square. As long as I am writing this correctly here, this has got to be correct. Okay. After said this, now my aim is not only to get C, but I also want to get the zeta values, is it not? So, from there only I will get my A0, A1 and A2, because what I know in my system is not C. What I know in my system is I am fixing up zeta. That is what we did in the last example also. We fixed up zeta as same for omega I and omega j. We inverted the matrix and we got A0 and A1, is it not? So, we know zeta, we will fix zeta. Okay. So, having said this, okay, I call this set of equations as 8. So, for nth mode, the generalized damping can be given by the following equation. Which is C, where I am using n, because nth mode, a summation of L0 to n minus 1. I am using the same equation back again here. I am rewriting it slightly in a different form. Phi n transpose Cl phi n. Where Cl is M inverse K of K. Hence, for L equals 0, L equals 1, L equals 2 and so on, I can get phi n transpose C naught phi n. Which will be phi n transpose C naught already I have here, okay, A0 m phi n similarly phi n transpose C1 phi n. I can rewrite slightly the last term as A2 omega square okay k by m omega square. And what is phi transpose k phi n? From the principle of orthogonality, omega square m, so also equal to omega square m, okay. So I can rewrite now this as further A2 omega square n, let us say rewrite it here, phi n transpose k phi n, which can be said as A2 omega n square or omega 4 mn. Because this will be omega square m. Hence, this was equation 10. Equation 10 can be rewritten as Cn L equals 0 to n minus 1, Al, I am using all these values here back, Al omega n to the power 2L m. Call this equation number 11. And damping ratio zeta is given by zeta n, of course, is equal to Cn by 2 zeta omega n, Cn by 2 zeta omega n, oh sorry, omega n mn, because T is equal to 2 zeta omega n. Substitute back for Cn here, omega gets cancelled, ultimately gets Zn as one by 2 of this half is here, summation of L equals 0 to n minus 1 of AL of omega n 2L minus 1 of L. No, Mn goes away, sorry, that is my equation number 12. So, I get the damping matrix from here, I get the damping ratios for different modes from here. Once you know all the ALs for different modes, you can easily find Ca. Now, there is a very specific problem associated with Caughey series. What is that problem? Look at this equation 12 or 11 and tell me what is the problem associated with this specific series of damping. There is a critical problem here. Look at the series and tell me what is that problem. So, this is AL omega n 2L minus 1 half of L0 to n minus 1, equation is fine, and 11 is 0 n minus 1 AL of omega n 2L Mn, fine. There is a very critical problem here. Let us check what happens when I put L is equal to 0 in this equation, L is equal to 0 in this equation, I will get omega to the power minus 1, is it not? So, I get 1 by omega. Let us put L is equal to 1 here, I get omega 1, okay, omega 1, 2 cube, okay. I am skipping in between frequencies, no? It is not covering actually all the frequencies. So, I call this as equation 12 is mathematically ill conditioned. It's mathematically ill conditioned, does not cover all the frequencies, actually skips. And how this will affect my calculation? If omega, omega 3, omega 5 are widely different by many orders. What do you mean by many orders? For example, this is 1, this is 15, this is 200, etc. Very widely different by many orders. Okay. This will not give you the correct representation of damping. Okay, that will be the problem. This will result in ill condition. That is the difficulty with this damping, but this damping is capable of covering all the frequencies as we saw, is it not? The damping ratios are skipped. See, I am not including the damping ratios of all modes, I am including only selective modes by order. Damping ratios are not included, okay. But here I can keep on adding from 0 to n minus 1, I will have all frequencies included, but the damping ratio contribution from all frequencies are not coming in the zeta value, is it not? That is the problem here, okay. So, let us pick up the same example quickly and try to solve for A0, A1 and A2 and get C matrix and see how this C is different from the last C matrix what we got in the earlier lecture. They are different, is it not? Because there we got only A0 and A1, I picked up only two frequencies omega 1 and omega 2. I showed that omega 3 zeta 3 is approximately equal to 5, it was around 6 point something, is it not? But here I will fix zeta for all frequencies same, okay, and get C matrix and compare how the C is different from the earlier C, okay. So, we are looking at the estimating of damping matrix in this problem, is it not? It can be either mass proportional alone, stiffness proportional alone, but it is not successfully operating in the practical considerations in experiments. So, we are looking for an amalgamated models from Rayleigh, from Caughey, and one more method which we will discuss on Monday's class. So, these are some interesting applicable practically possible methods for multi-degree freedom system. There are many more methods, we are not discussing all of them here. By sample I have discussed 3 methods, okay. I have discussed now 2, I will discuss one more method on Monday class. So, I will have 3 methods discussed, there are many more methods available, okay. So, let us do the same problem back. I have to retain this equation, I will write it or you will give me this equation when you do the problem, I will rub this. Do you have any questions, any observations in both these methods of estimating damping? Now, please understand, in all the problems in dynamic analysis where fluid structure interaction or material nonlinearity or geometric nonlinearity or dependency of restoring coefficients on responses, like we have seen in many of the offshore structures, estimate of damping is most critical. This is further critical if you are talking about response control of offshore structures. For example, you want to control the response, you have to play only with the damping coordinate. So, mass you cannot reduce, because if you reduce the mass, like complaint structures for deep waters like TLP, spars or triceratops etc., they will become highly flexible, you will not be able to install it. If you if you change the restoration matrix K matrix, the system will become very flexible, you will not be able to put a desired payload on the structure. So, K and M you cannot touch, because K and M are from the geometry, and geometry you are not altering, is it not? We are only altering the form. Remember, very importantly, in offshore design or in offshore evolution of platforms, we are not touching the geometry, we are only altering the form of the geometry by introducing hinges, by introducing teethers, by introducing external connections, by putting more legs etc. Is it not? We are only changing the form, structural form. Geometry may be square, you have the same diameter of the pipe cylinder as 12 meter earlier, now also 12 meters etc. To take the same structure to deeper and deeper waters, we have to have an innovative structural form, we are working only on that. So, K and M will actually not help you much to response control, right. So, if you are talking about let us say TMD, which we saw in the previous lectures of the same module, we have used unit mass dampers, there are many other ways by which one can control the responses, we have to play only with the damping matrix. So, estimation of damping becomes very important in the analytical as well as practical significance of offshore structures, okay. So, let us have the same example as we saw in the last lecture, just for comparison I am picking up the same problem. This was M1, M2 and M3 which were all equal to M, this was K1 equal to K, this was 1.5 K, this was 2 K, where M was 3500 kg and K was 1500 kilonewton per meter. So, I had omega 1 and omega 2 and omega 3 as 11.8 radians per second, 29.27 radians per second and 44.778 radians per second. By the way, have anybody verified whether these two answers are correct by the classical methods what we already know? This I have shown you yesterday, we derived this value from the Stoddard's method, but I wanted you to verify these two by either influence coefficient or matrix inverse methods to find out whether they are actually having the same value. Have you verified? Anybody? Has anybody attempted to thought of verifying it at least? See, this is where actually you are diverting from the original focus of the course. The moment you do not show interest in carrying dynamics as your classwork, at least take it granted your research will seriously suffer if you are working on dynamics, because the one which you do not do now you will never ever do it, because of two reasons. You will not have motivation to do, two, you will have no technical let us say lectural assistance to do it. The problem what you had or what you will have in future on estimating this will remain unsolved until you come out with some other parallel course like this or break your head try to solve it out. You will not be able to do it. I am repeatedly telling you, unless otherwise you do all these exercises very seriously, for 1 hour teaching of dynamics you must work at least 23 hours in your class before you come for the next class. If you do not do that, you will not be able to follow this course completely. So my objective will go waste, but still I am insisting at least today before you come for Monday, verify omega 2 and omega 3, are they correct or wrong, verify it. So now let us try to work out the values of A0, A1 and A2 to find out the C matrix from the Caughey's model. Rayleigh we already have. So we already know C matrix given by A0 of M plus A1 of K plus A2 of Km inverse K. I call this as equation number 1 for my problem. We already have the mass matrix, we already have the stiffness matrix, I do not have it here. What is the value stiffness matrix?
minus 1, 2.5, 1, minus 1.5.
And zeta n is given by the equation is half of summation of L 0 to 2, because it is 3 degree freedom system, n minus 1 AL omega n to L minus 1. So I can say, I can expand this and say zeta n is half of A0 by omega n plus A1 omega n. Okay, this is exactly what we are getting in the Rayleigh damping also, plus A2 omega n cube. So let us write this in a matrix form. So 2 zeta n is going to be okay, let us do it like this, twice of, I am taking 5% damping. So I say 0.05, 0.05, 0.05, that is what I am interested in now. Okay, I am fixing damping for all the frequencies same, which we did in the Rayleigh's case also, is equal to I should say this is 1 by 11.8, that is my omega 1, and omega 2, okay, let us complete this, 11.8 cube of A0 A1, is it not, that is the matrix form, and similarly 1 by 29.27, 29.27, 29.27 cube, and 1 by 44.778, 44.778, 44.778 cube. Okay, 5 minutes time, invert this matrix and get me A0, A1, A2 quick. So, what are the values of A naught, A1 and A2? Yes, A0, A1, A2. For A1, very high.
0.07, 3.9 to 10 power minus 4.
This one or this one? A1, 3.9 10 power
10 power minus 4.57 and 10 power
minus
minus 4.57
6. You will see that these values and these two values are closely matching with what we had for relays A0 and A1, and the contribution of higher modes is limited, okay, it is very low, but still substitute the above values in equation 1 and find C. So, it has got many multipliers, you have to multiply with m, k, then again do this processing and multiply with A2 and get C matrix, and of course C matrix will be now a 3 by 3 matrix which you can find. Okay, that is how I estimate the damping matrix using Caughey series, which is including the contributions from all frequencies omega 1, omega 2 and omega 3, keeping conditional that zeta is same or the damping ratio is same or it is uniform in all the modes of vibration. Damping ratio, not the frequency, damping ratio is assumed to be same in all modes of vibration. In the Rayleigh's case we could not do this more than 2, now in Caughey's case it is general, we can do for n minus 1 if n is a degrees of freedom, okay. That is the deviation between this particular method with that of Rayleigh, okay. Of course we cannot compare the damping matrix obtained from A0m, damping matrix obtained from A1k, damping matrix obtained from A0m plus A1k plus damping matrix obtained from A01, A1k, A2k, m in k inverse etc. We cannot compare them, they are all different formats because they are including different contributions of modal frequencies or modal damping ratios in your calculation. So, it cannot be compared, okay. But which one will use depends on the justification or the decision of the analyst, right. So, that is where we stop here. Now, the problem with this particular series is that it skips on a different frequencies contribution. forms an ill conditioned system. If you want to make it numerically stable, then I should include straight away the superposition of modal responses directly or modal damping ratios directly on my C matrix. That is the third method we will see on Monday. We will pick up one same example, we will solve this problem slightly in a different manner and see how I get C. So, I get different methods to estimate damping matrix, that is where we stop. Okay. So, these are the three methods we have for estimating damping matrix, which is commonly practiced in literature for structures which has wide spread of frequency ranges. We can go ahead with Rayleigh damping because we have got in TLP we have got two distinct set of frequencies, though we have 6 frequencies, we have got two distinct set of frequencies, one is stiff and one is flexible. So, I can easily handle TLP problem of finding C using Rayleigh damping. But if you do not have that facility in your geometric form of an offshore structural system, you can use Caughey series or you can use modal damping ratio series, which we will discuss on the next lecture, you can find C. Okay. Now, remember in this particular problem that C will get updated every time because K and M are changing and omega is changing. Even otherwise also C will get updated because M or K may change in a system when the system is under damage. Okay. So, C will get updated, right. So, once we discuss that on Monday's the next lecture, then we can speak about coming back to the original TLP problem. We have got M, we have got K, we have got f of t understood. Now, we will show how we have got C, then we will run the analysis using a specific iteration scheme because it is an iterative process, get the results and discuss them quickly from a paper. That is how we will complete the discussions on TLP and how f of t handles different kinds of forces like wave force, current force, earthquake force, stability forces, how it is handled and how it is modeled and how it is taken care of in the dynamic analysis. We will address that f of t part separately. So, that ends the discussion on TLPs. Then we will go to the next generation platforms where we will talk about triceratops, we will talk about perforated tensional platforms for response reduction control mechanisms. So, how the problem formulation can be done, just an idea. Then we will move this to the next module where we will talk about application of dynamics on simple manufacturing instruments, like I want to manufacture an accelerometer, I want to manufacture a displacement transducer, I want to produce, because accelerometers are costing around half a lakh when you import it from US. Okay. Can I manufacture an accelerometer? Can I have a instrument which can work as displacement transformer as well as accelerometer in different ranges? Can I manufacture it from fundamental principle of dynamics? It is very much possible, we can do. So, I will explain that concept in the third module, then we will move on to application of this for modal response estimations or participation factors doing some problems, then we will move on to the stochastic dynamics part, which is again an intensive research area in dynamics. That will how we will conclude this course around 47-48 lectures in total.